Okay. Okay. So I'll keep depressing a bit as I go, but we may as well get started now. So I'm Scott. I'm a second year medical student at Oxford, and you might have seen me from like biology tutoring as well. So I've done a bit of that. I did OCR tutoring for biology. Yeah, and I just basically tutor biology and chemistry for the company. And today we're going to look at some NMR. You should all hopefully know what that is by now, because the exam is on Monday. But this is basically just a revision session. I'm going to give you a few tips and tricks that can guarantee you get all the marks in these questions. Um, and yeah, like talk you through the steps of it. Because I feel like this is one of those topics that looks really complicated, and that's because it is, but there are ways through it. And before I start, I just want to emphasize something. This is an A-level exam, so it's not an Olympiad. And the difference between those two things is that in an A-level exam, it is possible that like they do want you to get the answers, whereas an Olympiad, they're like they put deliberately difficult questions that they want most people not to get. And I make that distinction there because often with A-level chemistry, it's very easy to become intimidated by it and feel like the question in front of you is impossible. But the important thing is that if you've revised effectively, if you have gone through the spec completely, you should be more than capable of getting the answer correct to these questions. So that's the thing to bear in mind there, is that it is possible to do really well. And I think the main thing is to just get like a solid technique when it comes to answering the difficult questions, and then you can be sure that you'll be able to get all the answers. So let's finish admitting a couple more people. The spec for today is here. I chose OCR spec because it's the biggest one for analytical techniques. Specifically NMR. However, I do emphasize that EdXL, which is what I did actually, AQA, all of the other ones, it's effectively the same thing. So, yeah, like this is useful for every exam board, is basically the point I'm making there. So you can see that what we're going to go through is we're going to look at carbon 13 and proton NMR. And then at the end, we're going to have a go at a few exam questions. I'm not going to go through the actual content of like infrared spec and mass spec because it's not on the agenda for today, but we will look at a few questions where you're required to integrate the different approaches. If you have questions throughout, please don't be afraid to ask. Um, yeah. Um, so yeah, let's get started then. The session is all in the chat. Yeah, feel free to ask questions as we go. I'll answer it when it's convenient though, just so we don't get interrupted constantly. But the session is an hour long. But if we finish a bit before that, I know you're all busy revising, so yeah, I'll try and get through it as quickly as I can. Let's begin. So, this is a bit of background to what NMR is, and you don't really need to know this, but it can just sometimes help you understand it a bit better. Because I think with something like NMR, if you just throw it at you, you're like, what is this? But if you understand like what you're actually seeing, where the signal is actually coming from, it can make you feel a bit more comfortable with it. So don't worry about memorizing like the word radio waves or magnetic fields, but just be aware that this is basically what's going on. I'll rush through the slide quickly because, as I said, it's not the most important one. But basically, atoms that have odd numbers of nucleons, so that's protons and neutrons, they have a property called spin. And if you put them in a magnetic field, they basically align with or against the magnetic field. And then you can fire radio waves at them. They absorb the energy of that, and then they jump from the lower to the higher magnetic field, lower to higher energy level, basically. And yeah, and so you can measure the difference between these two energy levels. So this is when it's aligned with the magnetic field, and this is when it's aligned against it. And there's an energy difference between them. The radio waves get absorbed, goes to the higher one, and yeah, you can record how much energy is absorbed, and that is what the signal in the NMR is. I won't spend too much time on that because, as I said, not very relevant for the exams, but it's good to know sometimes just so you understand what this signal is actually measuring. It's measuring the energy of the spin, basically, the energy level of the different atoms. Okay, so the first step with NMR is to be able to identify different environments. So what is an environment? It's basically in different molecules, you have, we're going to talk about carbon and hydrogen. You can have other NMRs as well, but at A level, you have carbon and hydrogen. And an environment is basically a unique place in a molecule. So I've chosen this compound over here. It's an ester and ethylethanoate specifically. And I want you to have a look at it. So we're going to start with carbon because that's a bit more easy than proton and MR. But basically, count how many carbons are in this molecule. Hopefully, you get four. So one, two, three, four. And what you basically want to be able to tell me is how many different types of carbon are in this molecule. So this carbon, if you like drew this carbon by itself, this I'll circle it over here. So this carbon over here, if you drew what it's bonded to, you can see it's got a double bond to an oxygen, a single bond to a carbon, a single bond to an oxygen. And if you wanted to, you wouldn't have time in an exam really, but if you wanted to, you could make a list. So double bond to oxygen, single bond to carbon, single bond to oxygen. This carbon over here has three single bonds to hydrogens and then a single bond to the rest of this molecule, basically. This carbon bonded to two hydrogens, bonded to a methyl group, bonded to an oxygen and the ester group. And then this one over here bonded to three hydrogens and bonded to the rest of the ester. So what is a carbon environment? Well, it's it's basically when the atom is bonded to make a unique environment is when the atom is bonded to different groups to any other carbon atom involved in the molecule. So the question I'm going to ask you just briefly is how many carbon environments are in this molecule? Hopefully, hopefully you should have got the answer of four. So yeah, four is the correct answer. And the reason I picked this molecule is because you notice it has two CH3 groups in it. But the point I really want to emphasize here, because this is a silly mistake that you might come across. I know someone just asked in the chat, am I going to go through silly mistakes? I will as we go along. So the important thing with this molecule is that it has two CH3 groups. So an easy mistake to make here is that these two carbons, this one, number one, number four over here, that they are in identical environments when they're not, because they are bonded to different things. Yes, they're bonded to three hydrogens, but the rest of the stuff they're bonded to, this one bond here, this one bond here, is different. So that's just something to really emphasize is that you have a different carbon environment. What about a proton environment? Well, it's basically the same principle. So you've got hydrogens over here, and hydrogens over here. So how many proton environments is that? Hopefully you get three. Yeah, hopefully you get three. Okay. And the thing with the protons is that obviously each carbon is bonded to multiple protons. So this hydrogen, this one, and this one are in the same environment basically, and that's just something to really emphasize. They're bonded. The carbon they're bonded to the same carbon basically. So that's how you can identify the proton environments. Um, Someone just asked in the chat, can you basically say that the number of carbon environments is the same as the number of carbons in a molecule? That's a really good question because the answer is very important. The answer is no. So I'll draw out a molecule over here. So let's draw, I'm not going to draw, all right, I'll draw this. So this is going to be propan 2O. Just imagine it's hydrogen. I'm not going to take too long. So I'm just going to, where I would do a line, it's where a hydrogen is basically. This is propan 2O, okay? And propan 2O has three carbon atoms, but it only has two carbon environments. It's got this one over here, but because this carbon and this carbon are bonded to exactly the same thing, they're bonded to three hydrogens and the carbon with the OH, they have the same carbon environment. Does that make sense? And the protons bonded to them would also share the environment as well, because they're basically bonded to the same thing. Um, okay. Uh, the chat's being a bit laggy. I'm trying to look at what the next question says. Um, oh, here we go. Um, okay, yeah. So this is just something to really emphasize is that the number of carbons is not necessarily the same as the number of carbon environments. And what you basically have to do is in your head, make a list. What is this carbon atom bonded to? And is it exactly the same as this other carbon atom? And the same for the protons as well. Um, does propan-2-ol have four proton environments? Yes, it does. Oh wait, no, wait, sorry, it doesn't. Uh, three. So this is a proton by itself. There's going to be a proton down here as well, those two. And then the protons of this one and this one over here, they're going to be the same. People are asking about splitting patterns in the chat, and I'll get onto that in a minute. Um, yeah, I just got to admit a few more people. So we're gonna start by looking at carbon NMR first, but then we're gonna head on to proton NMR. So yeah, we'll just got to admit a few more people. This is a lot of people. Okay. Um, so someone just quickly asked, is OH not in its own environment? The proton of this OH it is a unique proton environment. It would create a spike. So that's something we'll look at in a minute. I'm just going to move on from the questions now so we can make a bit more progress. Why am I telling you about environments? Well, in any exam about NMR, there's always going to be a mark for saying that the number of spikes equals the number of environments. So that's the first, if you're making a list of notes from this, that's really the first thing I want you to make a note of, is if you ever get a 6 marker or like a 4 marker about NMR, that you get a mark instantly for saying this trace shows 3 spikes, and therefore there are 3 carbon, 3 proton environments, depending on which type of NMR it is. Okay. Um, let's move on. Still more people joining, just gotta let them in. Okay. Now there's something just before we move on to looking at traces that always comes up in exams, and it is what is tetramethylsilane, TMS. TMS is this compound over here. And what's special about TMS is that when you're ever, imagine you're doing NMR in a lab, so you're a chemist and you're trying to work out what a molecule is. You add TMS into the mixture. And what TMS does is if you look at it, it only has 1 carbon and 1 proton environment. This carbon is bonded to 3 hydrogens in the silicon, but so are all 3 of these carbons. So it has only 1 carbon environment. And it's the same for the protons as well. So why is that really useful? It's because if you put TMS into the NMR machine by itself, it will produce 1 spike. And this spike just so happens to give out a really nice signal that we can base everything else off of. So the signal, if you put like, I don't know, like a random ester into the NMR machine, the signal produced by all of its environments is worked out relative to that of TMS. So we're going to look at a property in a minute called shift, which is what you see on NMR traces. And what you see is that in every NMR trace, there's going to be a spike at zero, a zero shift. And that spike is due to TMS. Everything else is worked out relative to TMS. So essentially, the units of what shift is it's the signal given out by this environment relative to that of TMS. And that's why TMS is really great. And often they ask in exams, why is TMS used? Not only is it useful because it gives out 1 spike and because that spike is very left, so it's very useful to relativize everything else to. It's also a non-toxic compound. It's non-reactive, it's inert. It has a really low boiling point, which is useful to distill it away from everything else so it can be separated and reused. And this is the really key point. It produces one strong, sharp absorption peak on the spectrum. So yeah, so chemical shift, which you might see as delta, is given relative to the standard, and the standard is the TMS spike. Um, yeah, so TMS is a volatile compound, has a low boiling point, which is useful because it distills off easily and can be reused. Okay, let's head on now. So now that we've got the basic principles underway, let's have a look at the first type of NMR that we need to be aware of, and that's carbon-13 NMR. Carbon-13 NMR it's not amazing because it only really tells you a couple of things. Proton NMR, specifically high resolution proton NMR, which we're going to look at in a minute, is a lot better because it has a lot more properties that you can convey information from. Carbon-13 NMR, there are 2 things. Imagine you're in the exam and you get a question about this. There are really only 2 things that you need to be aware of, and they are listed here. So the first thing, as I said to you a couple of minutes ago, the first thing you want to write is that the number of peaks that you see in the trace is equal to the number of carbon environments, okay? That's going to get you a mark instantly. So if you see 4 spikes, be like, this trace has 4 spikes, and therefore the molecule has 4 carbon environments. That's an instant mark. And as I explained a couple of minutes ago, number of carbon environments does not necessarily mean the number of carbon atoms, okay? Um, Someone just asked what solvent do we use for NMR? I'll get to that at the end. But yeah, so this is the first really key point, is that number of peaks equals number of carbon environments. Um, Now the second point is about the delta value. This is your chemical shift, okay? Um, and I explained what that was on the last slide. But basically, when I explained how NMR works at the start, where you have the radio waves and you get the energy changes, which is on not on the spec, but which is really important to get an understanding of this. Um, TMS absorbs very specific level of energy, and everything else absorbs a different amount of energy, and you can work out the energy absorbed relative to the TMS, and that will give you a signal. Now, in your data booklet, you'll see a table like something like this. And what that shows you is that you see the carbons in red in this data table. What it tells you is that those carbon environments produce a specific signal within that range where the white box is extending over. So I don't know. Is this a nitrile group over here? I'm just looking at it. This white box extends between a chemical shift over here and over here, and therefore, if you see a spike in this range, it could be this environment. However, key point over here is that often the white boxes overlap, and what that means is that you don't really get a definitive answer straight away. You're gonna have to use a lot more techniques because you get an overlap. So, like if you saw a spike in this range, it could be any of these three different carbon environments. Okay. Um, yeah, so just checking to see if we have any more questions. Uh, Sorry, let me just have a quick look. Uh, no, someone just said hi. Okay. I'm covering every exam board, but basically, someone just says they don't understand. Can you be a bit more specific? And then I can try and help you out. You do need to be able to know how to identify a carbon environment, and I did just go through that on the previous slide, but it's essentially you should make a list in your head of what is bonded to each carbon. If it's identical to a different carbon, then they're in the same environment. Um, oh, so you don't understand the shifts. Just to go through that one more time, then to make it a bit clearer. Basically, the way NMR works is it's about how much energy is absorbed by specific atoms, specifically carbon 13 and H1 atoms, and that in different environments, those atoms will absorb different amounts of energy. The energy absorbed by TMS is well known, and basically the energy absorbed by other environments. Um, can be worked out using an NMR machine. And then if you take that energy of the other environments and base it relative to that of TMS, it basically gives you a value that you can plot on a trace like this. So it's basically a measure of how much energy that carbon environment or that proton environment is taking up relative to TMS. You don't really need to know that much about it, but it's important to know that. Yeah, thank you, person, for answering that as well. Someone just asked why is TMS used as a reference. I did just go through that. So yeah, that's great. Okay, let's move on then. So two things you want to get in your answer for this are the number of peaks equals number of environments, and that the delta value or chemical shift represents what the environment is, but that there is overlap, so it's not perfect. Okay. TMS is tetramethylsilane, which is used in NMR. Let's move on then. I'm just going to go through this slide quickly and then I'll have a look at any questions afterwards, just because this is probably the most important slide of today. And this is about proton NMR. So we just had a look at C13 NMR. Proton NMR is better, okay? And the reason it's better is because you can get a lot more information from it. So, whereas before with the carbon 13, you had two real things that you could find from it, with the proton NMR, you're able to get four things. And I have listed those four things over here. The first thing is the same as before, that your number of peaks equals the number of proton environments. So, if you write that in the exam, instant mark. This trace has three spikes, and therefore this molecule has three proton environments. Instant mark, okay? Um, And then there's a few new things as well that we'll get into in a minute. But I just want to say point three over here is the same as with the carbon 13 NMR, that in your data booklet, you get like a table of what the different shift values are for different proton environments. And the same thing applies as before, that it can tell you which environment the proton is in based on where along the x-axis the spikes are. So what the chemical shift is, okay? So basically, with proton NMR, two of the rules are exactly the same as before. Number of peaks equals number of proton environments, and shift tells you what the environment is. Now, what can become a bit tricky is that there are two extra pieces of information that we can take away. The first piece of information is that in proton NMR, the area under the peak, so you get a bit of a spike like this. Let me just draw this out for you. You get a bit of a spike, something that looks like this on a proton NMR, or maybe it's split, which is something we'll look at in a minute. You get a spike like this, and basically the relative areas underneath the peaks tells you the ratio of protons in that environment. So there's one spike, and here's another. Now, I know that this is quite a bad drawing, but imagine that the area under this is double the area under this. Okay, and I know I drew that badly, but yeah. So area under this is uh, A. We'll call this spike A, and we'll call this one B. The area under A is 1 and the area under B is 2. So the area under this is double of this. And the information that you can gain from that is that the ratio of protons in environment B is double that of environment A. Okay? So that doesn't mean that you have two protons in environment B and one in A. It could do. What it means is that the ratio is 1 to 2. So you might have like 10 protons in environment B and 5 in A. So does that all clear? That the area under the peaks represents the relative ratio of protons in the different environments. Okay. So that is something that's a really important point. Now, in an exam, they're not going to expect you to, like use integration or whatever to figure out what the area under each peak is. But what they can often give you is they'll write numbers on the top of the spikes, and those numbers represent the relative areas underneath them. So you might see like a one, a two, a three, and that tells you that what the relative areas are between those different spikes, and therefore what the ratio of different protons in that molecule in terms of environments are. And there might also be something you come across called an integration trace. What is that? Well, often with the spikes, you'll see like a line that looks like this, and then it goes upwards and like this. You're probably not likely to see this in an exam, but just in case you do, you might see like a thing like this drawn in the exam. And what that basically tells you is that the uh, is that this length A and this length B, that if you measured them with your ruler, it would give you the relative ratio. So to make that a bit clearer, imagine A is 5 centimeters and B is 10 centimeters. That tells you that the relative area is 1 to 2. Okay. So you're unlikely to see that, but just in case you do, this is just measure of a ruler, find out what the relative lengths are, and that's the equivalent to the relative areas, which is equivalent to the ratio of protons in those environments. So that's area. Let me just have a quick look at the chat to see if everyone is uh, a bit sure about what that is before we go on to what splitting is. Uh, yeah, so I just explained the integration values usually, like almost every time, are just given as numbers above the spikes. But just in case they don't, that's just a bit of a background to it. Could give into. Okay. Uh, I'm gonna get onto exam technique in a couple of slides where I do literally have a slide about how would you answer a six marker on this. So just wait until then if that's okay. But the first thing is I'm basically just explaining the principles here of what proton NMR is, um, so that we can, when we get to the six marker, we're like a bit more sure about it. Uh, okay. So I'm gonna wait to look at the questions in a minute. I want to now go on to what splitting is. So often in your exam, with the carbon-13 NMR, you're only going to get spikes like this, where it's got like one tip basically. It's a mountain with one peak is the way to visualize that. Um, However, with proton NMR, you sometimes see spikes that look something like this or like this. Okay. And so imagine it's a mountain. This mountain has two peaks. This one has three. And what are the names for those? Um, Doublet is two. Triplet is three. Yeah. Quartet four. Quintet five. Like, yeah, the different names for them as well. But basically, it's the idea is that this has two mountains, two peaks, and this one has three peaks. And so, what is the relevance of this? Well, it's really useful because it tells you the number of protons in adjacent environments. Okay, so this is a new piece of information that we can take away from the NMR. So there is a rule called the n+1 rule. That is basically telling you, um, so what, so n+1, n in this case, is the number of protons on adjacent carbons. So with the triplet peak, we have three peaks in it. We have like three mountains essentially in this one spike. And according to the n+1 rule, n would be two here. So that means you have two protons on adjacent carbons. Okay? Does that make sense? So if you have a triplet peak, then according to the n+1 rule, n is equivalent to 2. And what does n represent? It represents the number of protons on adjacent carbons. So in this case, if you see a triplet peak, it means you have two protons on your adjacent carbon. Okay? If you have a quartet peak, so that's where you have four mountains in it, then that means you have three protons on adjacent carbons. Okay? And as I say at the bottom here, often with these questions, it actually is quite worth when you're doing the practice for these questions, just learning a couple of examples of common themes that they like to ask in exams. So the one that I always thought came up, and it comes up basically every year, is that the molecule will have an ethyl group. It might not, but like often it does. And if you have an ethyl group, so that's CH3, CH2. So it looks like this, where you have your CH2 over here, and then this carbon has three protons. I'm just going to ask you, just think the answer yourself, and I'll go through it in a sec. But what would, if it was literally just this alone, what sort of peaks would you be able to see for that? Um, yeah, you're gonna see a you're going to see two peaks because you have two proton environments, and they are going to be a quartet and a triplet. Why is that? Well, imagine this peak for this proton and its fellow protons in this environment. This proton's peak is going to be a triplet. And that's because on the adjacent carbon, this carbon over here, you have two protons. And that therefore n would be 2. 2 plus 1 is 3, and therefore you get a triplet. But for this proton, its peak is going to be a quartet. And that's because you have three protons on the adjacent carbon. N is 3, 3 plus 1 is 4, and you get a quartet. So I hope that makes sense. Yeah, so it's basically telling you how many protons are on the adjacent carbon. Um, uh, yeah, okay, so just to go through this one more time. Proton over here has a spike, and it's in the same proton environment as this guy and this guy over here. There are two protons on the adjacent carbon, and therefore n is equal to 2. 2 plus 1 is 3. Triplet peak for this one. This one over here is in the same environment as this one, but it has three protons on the adjacent carbon. N is therefore 3. 3 plus 1 is 4. Quartet peak. Okay? And the other piece of information that you'd get from an e-file group, so you've got the triplet over here, which represents this guy, and you've also got the quartet, something like this, which represents this guy. The other piece of information is the areas, which we just talked about. So for this guy and this peak, you're going to have an area of 3, and this one you're going to have a relative area of 2. And that's because in this environment you have two protons, but in this one you have three. So you have these basically two new pieces of information that you didn't get with carbon-13 NMR. The first one being how many protons exist in that environment, which is told to you by the relative areas. And the second one being how many protons are in adjacent carbons, which is told to you by the splitting pattern and the n+1 rule. Okay, let's just have a quick look at any questions. Uh, Okay, great. So let's move on then. I hope that all is clear. But basically, this is a very common thing OCR, EdXL, AQA, all of them like to have, which is that you get a pattern like this where you have a triplet with an area of 3 and a quartet with an area of 2, representing an E-file group. So if you see that, it's often, I'm just giving you that because it often comes up. So it's like a bit of a tip that can help you instantly get it. Um, okay, let's carry on then. So there's not really much more information that you need to know for NMR. It's a very applied topic as opposed to a content heavy one. People have been asking for a while now if I'll go through the solvents, and here it is. So let's just try and understand this. Imagine you were trying to work out the NMR trace of ethanol, for example. I don't know, like, or like an ester, it doesn't really matter. Which solvent would you dissolve it in? The answer is you wouldn't use water. And the reason you wouldn't use water is because water is H2O, contains protons, as the H is, H2, so it's got two protons in it. And they therefore would interfere with your trace. And therefore, you use a special type of water called heavy water. And heavy water is water, but instead of being H2O, it's D2O, where D is deuterium. What is deuterium? Deuterium is it's hydrogen with a mass of two. So instead of just being a single proton, deuterium is a proton and a neutron. So it's an isotope of regular hydrogen, basically. That's what deuterium is. And there's a special type of water called heavy water, where the H is replaced with a D, basically. And we can use D2O as our solvent because it won't produce a spike because it has an even number of nucleons. Other things you might use is CCl4. Just this is a proton NMR, by the way. That would probably interfere with carbon NMR. But the reason you would use this is just because it doesn't have any protons in it. So yeah, it's gonna improve like it's gonna reduce the interference you get. Um, yeah, I'm just gonna have a quick look at questions. Uh, Yeah, someone asked, I thought you use CdCl3. You can. Yeah, of course, that would work as well. Basically, the key point here is to say nothing that has pro hydrogen H1 in it, basically, because that would just interfere with your results. We need to know about TMS. You do. I went through that on an earlier slides. This is recorded. You can watch that. Um, uh, so only Yeah, so only molecules with an odd number of nucleons show a trace. That is true. So at A level, you need to know about carbon 13, 13 being an odd number, and hydrogen 1, 1 being an odd number, NMRs. There are other types as well. Like there's one for phosphorus, but we don't really care about that. The idea is that only atoms that have an odd number of nucleons, nucleon meaning either proton or neutron, only those sorts of atoms will be able to produce a signal using NMR. Um, CdCl3 is a solvent that has a carbon atom, a deuterium, and three chlorines. Um, yeah, that's a good point, actually. Someone asked, is it different solvents for polar and non-polar? Yeah, so CCl4 is non-polar, so it dissolves non-polar stuff better. And CdCl3, as Ashley has written in the group chat, is polar and so dissolves polar stuff better. Just going back to your solubility sort of stuff. Um, okay. So I've only talked about solvents so far, but as you'll probably see, there's a bunch of other stuff on this slide I'm going to go through now, and I haven't really touched on yet. Let's have a look. So, as I said, I did EdXL back in the day, and this wasn't actually on EdXL, I don't think. I don't know if they've updated it now. This might not be on all the specs. I would double check that. This was on OCR though, because that's the most popular one, so that's why I chose to follow their spec. But this does apply to every exam board. There's basically a principle called proton exchange. Um, so basically, what proton exchange is that if you have molecules that have an OH group, so an alcohol, or an NH, so an amine group on them, um, that there is a property that if you dissolve them in D2O, that their proton basically gets switched out for a deuterium. And what that does on the NMR trace is it's going to remove the spike from the OH or the NH group. So whereas initially, if you dissolved it in a different solvent, I must say, if you dissolve it in a different solvent, the OH group or the NH group is going to produce a spike on the spectrum. So like this spike over here. Now, if you just added a couple of drops of D2O to it, um, that's going to cause an effect where this H over here gets switched out for deuterium, and therefore it's no longer going to give a signal on your NMR, and yeah, it's going to remove that spike. So that's just a phenomenon that OCR seem to care about. Um, uh, yeah, back in the day, yeah. No, it was 2 years ago, so it flies quickly. Um, D is a hydrogen with a proton and a neutron, so it's an isotope of regular hydrogen. Um, okay, let's carry on. Yeah, you write D instead of H. So instead of H2O, it would be D2O. Um, okay. Is it really hydrogen then? Well, that's something I don't even know. I don't even know how to answer that. Let's just carry on then and get on to some exam questions. Um, oh wait, there's this thing first. So just before we move on and look at a few applied examples, something I really want to get across is that often you see NMR not by itself, but with reference to other techniques as well. And what you basically need to be able to do is you need to be able to understand all of the different things at once and be able to apply them to get an answer. So, what are the sort of things they're going to give you? They can give you like percentage composition data, they can give you the mass spec, they can give you the IR spec, and they can give you the NMR. They can also give you chemical reaction stuff as well. So, like, they might tell you this reacts with Tollens reagent or this doesn't react with Tollens reagent, and you can get information from that as well. So, stuff like that, that's just an example. And the best techniques do this, often they'll do it step by step. So, the exam board will guide you through the question one bit at a time. But if they don't, the best way to do it is probably to go in this order, where you use percentage composition data. So, like, yeah, I'll go for an example of that and you work out the empirical formula from that. And then from that, you use the mass spectrum to get the MR of a compound. You can, using the MR and the empirical formula, you're able to deduce the molecular formula because the molecular formula is going to be a multiple of the empirical formula. After that, you can use the IR spec, and uh, that will narrow down which functional groups are present. And then after that, you can use the NMR to extract any further information. Um, okay. Just disabled annotation for others. Okay. So yeah, that's basically how we do combined techniques. And I'll go through a few examples of this. Um, I'll go through a few examples of this just so we can really get the exam technique down. Um, so in MR, in mass spec, yeah, like the furthest. So that you get the furthest peak, which is the molecular that is the it tells you the MR of it. But you occasionally get this phenomenon sometimes in exams where there's a tiny peak, which is the n plus one peak, as someone has answered exactly. Um, yeah, so it's the big one on the right. Okay, on the big one, yeah, okay. Let's move on to the exam questions then, and let's go through the exam technique. Here is an example of everything I was just talking about. Basically, I know this is quite a lot of information, so we're not going to like spend a lot of time, where I'm going to tell you write down your answers for this, like, and spend 10 minutes on it, and then we'll move on and look at the answers. I basically just want to make sure we know what sort of technique we're going to use here. So I'm not looking for you to get the exact answer, but I want you to basically be able to understand how you would approach this. So this is the percentage composition thing I was talking about. Where the first step they want you to be able to do is they tell you like the percentage composition of mass by mass of compound X, and they want you to calculate empirical formula. And what you would do there is you would do like the percentages divided by the relative atomic masses, and then that will give you a number of moles, and then you can find the ratio between them. So that's a fairly basic thing that they do at even GCSE, and that will give you the empirical formula. You now go over here to your mass spec, where 88 is your molecular formula peak, the M peak, and yeah, and you can deduce the molecular formula from this. So uh, basically, to do that, you would find the mass of the empirical formula and do 88 divided by that. And that will tell you how many units of the empirical formula are in the molecular formula, giving you that. And then you go onto the IR spec and you use your data booklet and get the functional groups, and then you can look at the chemical reagent stuff. Okay. Um, okay, I'm just looking through the questions. Okay. So that's basically how you would go about answering this. I'm not going to tell you to have a go because that would take too long. Um, Also, my phone's over there. Does anyone have the time actually? Can you just write that in the chat because I can't check on here. Just so I know like how long we have left. Okay, 41. Thank you. Thank you. Yeah, okay, great. So we've got 90 minutes left. Um, so we're gonna have a look at a few more examples, but basically, hope that makes sense. Hope this makes sense as well. Hope the IR spec makes sense. You basically open up your data booklet, see which functional groups that would be in check with the molecular formula and that fall in this range occur, and then you have a look at the chemical reaction stuff, and that can really confirm the functional groups for you. Um, Okay, so there we go. That's great. Let's look at this is what the mark scheme said for it basically, and it's basically everything I just told you, which is you do the percentage composition by mass divided by the relative atomic mass, gives you number of moles. You find the ratio between these, gives you an empirical formula. If you found the mass of that compound with just the empirical formula, it would be 44, but the molecular formula is going to be 88 over here in the mass spec divided by 44. That tells you get 2 units of the empirical formula in the molecular formula. And so, yeah, it tells you what the molecular formula is. Then you go to the IR spec and you find that those are what's in the range. And then you talk about all the chemical reactions, which is something that's beyond the scope of this session, because that's looking more at, your pure organic stuff. But yeah, we don't really have time to go into why that is today. But you can basically deduce a bunch of stuff from that. Um, Basically it's a neutral compound, so it's not carboxylic acid. And yeah, doesn't react with tollins, meaning that it's a ketone, not an aldehyde. It has a ketone group. And then it reacts with acidified dichromate. And so it's an alcohol, specifically a primary or secondary. But it also has that ketone group from over here. Okay. Just checking through the questions. Uh, How does the position of an electronegative atom affect the shift? That's a good question. Um, Basically, I don't really want to answer that because it might confuse some people because it's not really on the spec. But essentially, what affects the signal of where the spike occurs is an effect called shielding, which is the electrons surrounding the atom have an effect with the energy and stuff and the magnetic fields, which is, yeah, don't really need to know that much about it. But if you have an electronegative atom, it's going to affect the shielding effect just by pulling on the electrons. Um, yeah, so don't worry too much about that, but that's a bit of why that is. Um, okay, let's move on. Next question. So this is continuation of the previous question. Just to remind you of what we found in the previous question, is that it had a it had a molecular formula of where it had a molecular formula of C4H8O2. Okay, so that's the first thing to make a note of because I just couldn't get it all on one page. So what was it? C4H8O2. C4H8O2. Ooh, okay. Uh, Ignore that. Let's go. Sorry, I'm having a bit of a tech thing over here. C4H8O2. That's your molecular formula. Um, and that's something you would have worked out if you did the previous question. And then you also have an alcohol group and a ketone group. So that's what we've worked out using the previous questions. And now what you need to do is you need to do a high resolution proton NMR of that compound, um, and you get this trace. And then tells you what the relative areas as well, just a bit more extra information. And what they want you to do is it's a six marker where they want you to figure out the exact structure of this compound using what you've done in the previous questions and the trace above. So I'll give you just a few seconds just to have a think in your head of what sort of things you would say, and then I'm going to go through how I'd approach that and how you'd approach these sorts of six markers in general. So just give yourself a couple of seconds just to have a bit of a think through that, and I'll have a read through the questions in case I missed something out when I was talking. Okay. Okay. Yeah, I'm not expecting you to like write down an answer or anything. I just wanted you to like think what sorts of points would I say in this situation. And basically, this is just to really make sure that the exam technique is fully there. As I said in a few slides ago, proton NMR can be divided into four rules, okay? And here are the four rules over here. Number of peaks, ratio of peak areas, shift, and splitting, okay? And that's how I would structure the answer. So to be more specific, I would start my answer by saying uh, compound X contains four proton environments because there are four peaks. You get a mark just for saying that. Um, and as it says, they sort of give the answer away with this over here, but they're telling you what to refer to. And if you do that, you're going to get the marks. So you'd start with the number of peaks and how that represents the number of proton environments, mark there. You could then talk about the relative areas, which they tell you over here. So 1, 1, 3, 3. And you have eight. Bear in mind, this compound we worked out has eight hydrogens in it. Okay, so it's got eight hydrogens. 1 plus 1 plus 3 plus 3 is eight, meaning that this is literally telling you how many protons exist in the environment. There's one proton here, one here, and three here. Okay. Um, and so you can literally write that down. If you wrote down what I just said, that's going to get you a couple of marks as well, just by saying that you have one proton in environment J, one in K, three in L, three in M. And that shows that you understand what the areas are showing. The next thing is to talk about the splitting patterns, and you can basically just say the trace shows a quartet, two singlets, and a doublet. This shows that the protons in environment J are adjacent to a carbon with three hydrogens. Those in K and L are adjacent to a carbon with no hydrogens, and those in M are adjacent to a carbon with a single hydrogen. And so hopefully you've gained some information from that already. You can also look at the shift values as well, and that's going to tell you what each environment represents. Sometimes it's a bit dodgy though, because as I said, shifts overlap with each other, so it can be quite tricky to work out, but it's definitely worth making a mention of shift if you can. So yeah, that's basically how you would structure your answer. You'd start by talking about number of peaks, you'd go on to the relative areas, you'd go on to splitting, and then if you can, you talk about shift as well. You don't need to here because they don't ask you to, but often you do. After that, you should hopefully be able to um, coordinate all that information together with the stuff on the previous questions. So like the fact it contains an alcohol and a ketone, and that should hopefully allow you to get to a molecule. So if you just want to take a couple of seconds now, just to draw out what you think that molecule might look like, and then we'll go through the answer on the next slide. I'm just going to have a quick read through the questions first, just to check that everything's okay. Just this is a question I just want to clarify. Someone said, are the number of peaks the carbon environments, or are a number of carbons then the splitting the number of hydrogens? So in a proton NMR, there's nothing about carbon, okay? So always read what it says at the top. It says this is a high resolution proton NMR. So it's only talking about hydrogens. Other questions might be about carbon 13 NMR, in which case it's only about the carbons. And the takeaway is that the relative areas represents how many protons exist in that environment, whereas the splitting pattern tells you number of protons that exist on the adjacent carbon. The word adjacent meaning the carbon next to right next to it, basically. So, for example, if I drew this out, where you've got a CH3 and then a CH2, as I drew before, um, okay, if I draw this out, the peak for this proton over here will have a relative area of three because three protons exist in this environment, one, two, three. Whereas it will have a splitting pattern of triplet because there are one, two protons on the adjacent carbon, and you follow an n plus one rule, n being two, and therefore n plus one being three, so you get a triplet peak. Okay, so that's just to clarify that point. Uh, Do they give you the molecular formula? You worked out on the previous questions. That was what we just looked at before. So I just wrote it down for you there because I couldn't fit all the information on one slide on PowerPoint. Um, okay. Would I recommend drawing a table for different things? You can do, but personally, I'd avoid that. The reason being that often in six markers, there's a mark for just like how you write, as like your quality of writing. So it's good to just write it out in full sentences because that can help you get that extra mark. If you did do the table, it can be helpful to get you like 4 or 5 marks in the bag. But if you want to get all six, then I'd write in full sentences. Um, you can still get marks if you weren't able to figure out the structure. Yeah. So it's about how you approach the question as well. So like if you understand what splitting and peak areas are showing. Um, You can draw a table though, like to help with your thought processes. But like if you have time, just I would just do the actual writing of full sentences. How do how I got the splitting patterns on the graph. It's a quartet, singlet, singlet, doublet. That means this environment's next to a carbon with three protons. These ones are next to a carbon with no protons. This one's next to a carbon with one proton because the splitting pattern follows the number of protons on the adjacent carbon plus one. Um, Okay. How is K a singlet? Because it exists it's probably the OH group. And that is if it's attached to an oxygen, it just produces a singlet peak because there's no hydrogens adjacent to it. Um, okay. Let's carry on then. Here is the structure. Just so hopefully you might have got something like that. If you didn't get that exact structure, don't worry about it. My biggest tip is to practice these questions. I'll also go through a bit more technique. The only thing is you actually, if you didn't know that structure, but you still mentioned everything I said, you can still get a lot of the marks, 4 or 5 or 6. The reason being that look at the mark scheme. So like you get this one over here just for talking about how many peaks there are. You get if you talk about the n plus one rule, you can get quite a few marks. And then these ones come from simply drawing a structure as well. So you might not have basically been able to draw it exactly like this, but if it's close enough, you're gonna get quite high. So don't worry too much. Um, Okay, let's just have a quick more read of the questions. Okay, let's move on. Here is a bit of an exam technique thing that I put in just to talk about these six markers in a bit more detail. Basically, I would sit there. You can draw a table just to help with your thought processes, and hopefully you can try and work out the structure from that. The best way to be able to do that quickly is, as I said, practice. There's not really any other way around it. The more practice you do, the more accustomed you become to seeing different spikes representing different things, and that will mean that you're able to do it more quickly. I believe that everyone could do this if they had like infinite time, but to be able to do it rapidly in exam conditions, you really just have to practice it a lot. So hopefully you get the structure, and now you've got to explain yourself. I would talk about the 4 rules that I mentioned at the start of this session, and then you can give explanations for how those 4 rules allow you to get to the displayed formula that you got to. So for example, on the previous question, um, you could say something like, um, you could literally just apply the n plus one rule to peak M, which was a doublet, and say that that means there's a single proton on the adjacent carbon. Okay. Uh, I'm not sure when the recording will be available. I'm sorry. Yeah, I'd speak to Ojas about that. Okay, let's carry on. Let's have a look at a couple more questions. That was the only six marker I'm going to go through because like once you've done one, like what else am I going to really be able to tell you in terms of answering six markers? Apart from give the structure, write out the four rules I said and how they are related to the data they give you. So if it has three spikes, say the three peaks represent three protein environments, and then relate it to the specific compound that you drew. Here is another question you might want to have a look at. I'll just give you a couple of seconds to think, maybe like a minute or so actually, just to think through how you'd approach something like this, and then we'll look through the answer. What are the four rules? Number of peaks equals number of environments. Relative peak area equals relative number of protons in each environment. Splitting pattern follows an n+1 rule and tells you how many protons are on the adjacent carbons. And shift is tells you what the environment is. Those are the four things you're going to be able to deduce from an NMR. Oh, this is a really good question. Someone just asked if you have two carbon in envi environments in the same shift, does it just get a big spike? So that's a good question. At A level, it probably they'd be a bit more careful about it to avoid that happening. It wouldn't. It would look in a real thing. It would look quite messy where you get like an overlap between the spikes probably. You're unlikely to encounter that at A level though, just because that would make it really confusing. So yeah, so I wouldn't worry too much about that. The thing is though, carbon NMR, the only two pieces of information you can get from that are the number of environments and what the shifts are. Okay, so you unlike proton, you don't get the splitting or the relative areas. I don't know if there's a feedback form, but if there is, be nice. Thank you. Yeah, let's have a look at the answer for this. Um, oh wait, there's one more. Oh wait, why did I not put the answer? Oh no, I did. That is the answer. Okay, good. Yeah, so hopefully you can see that. Um, yeah, let me know if you have any questions about that, or hopefully it should be quite clear. Um, yeah, let's just go back to this one. Yeah, so hopefully you can work this out. Let's do like splitting over here, just making sure you're aware of the n+1 rule. Um, okay, so hopefully that makes sense. Let's go on to a final question. I don't know what time it is. If someone wants to write that in the chat again, because my phone's over there and I can't get out of the chair. So yeah, just someone. Thank you. Okay, yeah. Well, quickly, if it's 59, I'll just quickly just have a look at this one, and then yeah, that's basically the end. Let me know as well if you have any final questions before we end it. The last thing I would just say is, um, as I said at the very start of this isn't an Olympiad, which means they're not trying to catch you out. And that if you have revised effectively, you should be able to have a decent attempt at these questions. Just in terms of framing your answers, remember, always relate back to the rules that I explained, and making sure you mention all of them in your answer. And that way you can gain marks without accidentally missing stuff out. Okay, and people are still joining now, with 1 minute to go. Uh, you don't get splitting patterns on carbon NMR. So proton NMR is better because you get four things from it: the splitting, the relative areas, number of environments, and the shift. Carbon is only the shift and number of environments. Okay. Um, okay. So let's have a look at the answer to this one just quickly because I know you want to go off and revise. Yeah, it's basically we've already given examples of this. It's a phenol and a ketone because it's weakly acidic, and because it reacts with, um, and because it reacts with you have to talk about the 2,4-D MPH and the tolerance reagent, and then you do the NMR, and you should hopefully get something like that. Let me know if you have any questions. Um, What's my biggest advice for paper two? As I just said, I think the best thing you can actually do is practice, which sounds cliche, but like it's realistic. Like if you do a lot of if you go through a lot of questions for it, if you make sure you've done as many past papers as you can, then you just mentally become much stronger at it. You're able to do it quicker. As I said, if you've revised well, you should be able to do all these questions correctly if you had infinite time. The challenge is being able to do it in exam conditions. But the more you practice anything, the quicker you're going to become at it. So that's my biggest piece of advice. Because also, if you practice it a lot, often the same sorts of stuff repeat itself. So like, for example, I don't know, like in infrared spec, for example, you always get that broad peak if it's got a carboxylic acid. Stuff like that, there's a lot of stuff like that in A level chem. And it just becomes instant if you do a lot of practice papers for it. So that's basically the sort of thing that it just makes you become much quicker and effective at it. And also, I would say, as you do the past papers, when you make sure to mark them. That's the most important thing. Make sure to mark them and mark them in green pen. And make sure that if you miss something out, that you write that down in green pen where you should have put it. What that does is once you finish the past papers, you can just flick through them, looking at where the green pen is, and that will basically allow you to learn from your mistakes. And if you identify a similar question in the future, to be able to have a decent go at it. I hope that helps. Yeah, that's basically the end of the session. Let me know if anyone has any